Hey there folks, In the last video, I continued to build out the wall-mounted computer frame by adding some carry handles so that I could pick it up and maneuver the unit around. That capability will sure come in handy when it comes time to mount it. Next, I skinnied down an alpha-cooled distro plate using my Dremel, alleviating a particularly frustrating characteristic as it relates to purging trapped air when filling the loop. Then I performed an initial radiator cleanse to get any gunk out that might be present. Spoiler alert, there was! Finally, I made a decision on which NVMe slot to install the primary hard drive in, reconfigured a Barrow digital Flowmeter to work in a reverse flow orientation, and finished the day by installing the water cooling loop on the frame. In this video, I'm going to be building and installing the door to the front of the frame, 3D printing several smaller parts for wire management, and getting the power delivery in place for the fans. Completing these tasks will surely see us doing a barrel roll toward the done nebula. The first festivity on the docket is to create not one, but two offset arms that the front door will be mounted to. To make these, I'll cut 4 links of aluminum that are 1 5/8 inches long, and 2 links that are 6 3/8 inches long. A couple of inside corner joints will be used to attach these pieces together to form a shallow U shape. I'll slide a leg of an interior corner joint into a 1 5/8 inch length and slide the other leg into one of the 6 3/8 inch pieces like so. While applying a crisp bit of downward force on the longer piece, I'll use a hex wrench to lightly thread the set screw. Now I'll insert another corner joint into another short piece and slide it onto the other end of the assembly. With both smaller pieces attached, I'll use the hex wrench to Jason Statham everything into place. Once completed, the offset arm now looks like this. To build the other offset, I'll simply repeat these steps, achieving the glorious outcome of having 2 identical offsets. Since these offsets are going to serve as the point of attachment for a hinge door that has a couple of 120mm fans attached to it, I want to build in as much vibration dampening as I can. To that end, I'll be applying a thin layer of rubber to the areas where there is metal-to-metal contact. The rubber I normally use for vibration dampening is too thick for this particular use case. So this time I'll use a sheet of nitrile Buna-In rubber that is 1/32 of an inch thick with a Shore A rating of 60. I need 6 total pieces of rubber, 2 strips that measure 3/4 of an inch by 6 3/8 inches, and 4 strips that measure 3/4 of an inch by 1 1/4 inches. I'll start by cutting 3 links of rubber that measure 3/4 inches by 6 3/8 inches. 2 of these strips will be used as is, while the other strip will be cut into the 4 smaller 3/4 by 1 1/4 inch pieces. Using a ruler and pencil, I'll put marks on the rubber sheet and then cut them out using a pair of sharp scissors. With the strips cut, I'll add some heavy-duty double-sided tape to 2 of the links of rubber and attach them to the outside edge of each offset. Then, wielding my legendary air piano skills that have netted me not 2, not 1, but 0 world championships, I'll press down on the rubber to ensure adhesion across the entire surface. Since rubber will often stretch under the slightest duress, if I end up with a small bit of overhang like I did here, I'll use a razor to trim the excess off. Here's how we're looking with both pieces of rubber attached and the edges cleaned up. On the third strip of rubber I previously cut, I'll put marks at 1 1/4 inches, 2 1/2 inches, 3 3/4 inches, and 5 inches, and cut along those lines with scissors. For each of these smaller strips, I need to punch holes to account for the pass-through of the hinge screws, and those holes need to be centered on each piece of rubber. Using the ruler again, I'll put a mark on the top and bottom of each strip at 3/8 of an inch, and then connect the 2 points down the center. I'll be using these small hinges to add the door to the frame. They measure 1 1/2 inches by 1 3/16 inches and attach using countersunk or flathead M5 screws that measure 10 mm long. To mark the hole locations, I'll set a hinge down on each piece of rubber, align the center line mark to the center of each mounting hole, and then trace the inside diameter with a pencil. With the holes marked, I'll use a 1/4 inch leather punch and hammer to tap through the material and remove the hanging chad. Once the holes are punched out, I'll mark and cut 1/8 of an inch of the remaining rubber off one long edge. It doesn't matter which edge this material is removed from. Punched and cut but not bleeding, the 4 pieces of rubber now look like this. In preparation for building the door, I'll cut another section of aluminum that measures 6 3/8 inches long. Now I'll lay one of the offset arms flat and put a mark 1 1/2 inches in from each end. These marks are the points at which the inside edge of each hinge will sit. Next, I'll roll in a couple of T-nuts, situate the inside edge of the hinge at the 1 1/2 inch mark, and push the T-nuts with a hex wrench to align with the holes in the hinge. With the nuts and holes lined up, I'll lay the rubber on top of the metal, with the shortened side facing the middle of the two 6 3/8 inch sections of aluminum. Then I'll put the hinge on top of the rubber and lightly thread both flathead screws. Once those two screws are started, I'll repeat these steps for the holes on the other side of the hinge. The shortened edge of rubber will also point toward the middle, so as to create a trough directly underneath the hinge element where there is no rubber. It is critical for the edges of the 6 3/8 inch pieces of metal to be in alignment to ensure the door will open and close without issue, so I'll check throughout the process that I'm staying in alignment. Once I've confirmed everything is sitting Gucci, I'll tighten the screws down fairly tightly. I'm using the term fairly tightly here with the following consideration. Since there is a strip of rubber under each side of the hinges, if I tighten the screws down completely, the rubber will deform and the door will sit out of balance. My goal here is to get them tight enough that they'll stay put, but not so tight as to cause imbalance or misalignment between the components as they all come together. Now I'll repeat these steps to add the second hinge to the offset. We've now got smooth swivel action between the two longer pieces of metal on the assembly, and it's time to attach it to the frame. The offset with the hinges will be added to the frame on the front left side, pressed directly up against the edge of the motherboard tray metal here, while also maintaining alignment with the vertical support bar behind it. I'll roll in a couple of T-nuts and lightly thread on the smaller silver brackets using M5 8mm screws. Then I'll insert a T-nut into each short leg of the hinged offset, hold it with the legs above and below the two silver brackets, push them into position so they align with the silver bracket holes, and attach using M5 8mm screws. That completes adding the hinged arm to the frame. As you can see here, there's about a 1/4 inch of clearance between the bottom of the carry handle and the top of the rotating arm. I'll repeat these same steps to add the other offset arm, sans hinges, to the right side of the frame. With both offsets attached, I'm going to construct the remaining perimeter of the door. To do that, I'll cut 3 pieces of aluminum, 2 that measure 16 inches long and 1 that measures 4 3/4 inches long. To connect the pieces together, I'll use an inside corner joint in this arrangement. Once put together, I'm left to bask in the beauty of what could pass for 2/3 of a metal cricket stump set. With the outside perimeter completed, I'll attach it to the hinged arm. First, I'll pre-position into the open ends of the door an interior corner joint, and then slide what will be the top arm downward into the hinged arm slot. Slide the door down so the bottom corner joint extends past the bottom opening, and then slide the bottom back up to insert that joint into the slot as well. For temporary support on the other side of the door, I'll use a trigger clamp to lightly hold the door and offset metal together. It's important to leave this clamp a tad bit loose, so the whole assembly can shift around to get it situated into that just right position. Back on the hinge side of the door, I'll insert M5 set screws into the top interior corner joint and tighten those down completely, making sure to keep each edge of the metal aligned with the offset arm behind it. I'll repeat this procedure for the bottom corner joint, thus completing the full install of the frame's front door. Now's a great time to take Ocho Cinco's advice and attempt to shut the front door, to make sure it does actually shut, and is perfectly aligned on both sides with the offset arm. To wrap this part up, I'll use a millimeter ruler to measure the distance from the front edge of the motherboard tray metal to the front edge of the door on both sides. On the right side, it's 83 millimeters from edge to edge. Upon measuring the left side, I am delighted to discover that the distance is also 83 millimeters. As FPS Doug might say, boom headshots all around. With the door functioning like any self-respecting door would, I must tame its desire to open unless specifically directed to do so by yours truly. I've printed these simple door clasps that will serve just this purpose. One part attaches to the right side offset arm, and one piece attaches on the right side of the door, and they share a common through-hole position with a diameter of 4.05 millimeters, into which a 4mm by 40mm clevis pin will lock the door into place. The clasps themselves have a small gusset wedge where the vertical plate meets the horizontal body for a little added support. On the offset arm, I'll put a mark at 42.5 millimeters down from the top, and on the door metal, I'll put a mark at 112.5 millimeters down from the top. Next, I'll roll in a T-nut into the offset arm channel, position the clasp with the through hole on the left, and lightly thread an M5 8mm screw. Then I'll insert another T-nut, push it into place with a hex wrench, and lightly secure another M5 8mm screw. I'll repeat these steps to attach the other clasp on the door side, with the only difference being that the through hole is now facing up and is on the right side. Once both clasps are attached, I'll insert the 4mm by 40mm single hole clevis pin down the through holes and into both clasps. With the clevis pin in place, I'll slide the top of the offset side clasp down to the mark we made earlier at 42.5mm and apply copious rotational force with the hex wrench to secure the screws in place. Next, I'll push the bottom of the door side clasp to the mark at 112.5mm and then tighten those screws down completely as well. I'll pull the clevis pin in and out a few times to make sure the action is smooth and that the locking action does not leave any wiggle room for the door to exist in a loosey-goosey sort of state. At this point, I need to do what I like to call undoative work. That is work that must be undone to a degree to move another part of the build forward, but was previously not done until a higher level, more important step was completed first. In this case, I need to put a separation bar on the inside of the door metal, but I really don't like to do this until I've fully formed the door and added the clasp, so I can proceed knowing that the construction of the door itself is sound and without fault. I'll pop the clevis pin up, remove it from the clasps, and open the door. Now I'll cut another section of aluminum that measures 4 3/4 inches and insert an interior corner joint on the top and bottom like so. Now I'll remove the 2 set screws from the corner joints that are holding the piece of metal on the right side of the door and wiggle it free from the door's long loving arms. Using gentle force, I'll insert the separator bar into the door arms with the corner joints oriented like this, and then reinsert the piece of metal that was removed. Holding the door firmly closed, I'll start to re-thread the set screws on the bottom bracket. Since the set screws have already been tightened down once, they now have a pilot divot to follow and will go back to their original position as they are screwed into place once more. With the bottom set screw secured, I'll re-add the set screw at the top and the door will be back together. As you can see, the door still closes beautifully, and the clevis pin is in perfect alignment for the clasp to solidly latch the door closed. Next, I'll work on adding the fans to the door, which will cool the SSDs. I've designed these simple mounting triangles that align to the 120mm fan mounting holes and the channel in the aluminum. In total, I'll be printing and installing 4 of these triangle shapes, 1 at each corner of the fan area, and 2 pentagonal brackets that will bridge the middle of the 2 fans together. When printing these particular brackets, I dial back the ironing settings I typically print with to attempt to emulate a sort of brushed metal look across the surface of the brackets. This does cause some deeper lines to remain on the surface of the printed pieces, but in this case I think the look fits the motif of the build. To prevent as much dust from blowing over the SSDs as possible, I'll be using these Silverstone SST-FF121 ultra-fine fan filters. I'll be using the same fans here as I did on the Radiators, which is the 120mm Arctic P12 PWM variant. This model has the ability to daisy chain a number of fans together, but I'm not going to use that feature. In general, I prefer to run each fan's power cable all the way to the power source, instead of daisy chaining them together as often as possible. First, I'll roll in 3 T-nuts at these locations, and lightly thread an M5 8mm screw into each hole of the triangle bracket in the top left corner. I'll add another bracket along with 3 T-nuts and screws in the bottom left corner. To get the first fan in position, I'll angle one up and through the door opening, with the power cable positioned in the upper left corner. Next, I'll position a Silverstone fan grill between the fan and the corner bracket, and then insert an 832 screw that is 1 1/2 inches long in each of the remaining holes in both brackets, being sure to push the screw all the way through the holes on the fan. To attach the bottom middle bracket, I'll roll in 2 T-nuts in the slot, position the bracket holes over the nuts, and insert 2 M5 8mm screws. Leaving the screws a little bit loose enables me to slide the bracket back and forth in the slot. I'll repeat these steps to attach the middle bracket on the top bar as well. Once both brackets are loosely affixed, I'll massage their position until the holes align with the mounting hole on the grill and fan, and then insert another 1 1/2 inch 832 screw. The second fan can now be slid up and into position next to the first fan, a dust filter situated between it and the brackets, and 2 more 1 1/2 inch 832 screws pushed through the mounting holes. The power cable for the second fan will also be located in the upper left corner in relation to the door. Now I'll roll in 2 more T-nuts into the top and bottom horizontal slots of the door metal, and 2 more T-nuts into the separator bar. Then I'll align another triangle bracket in the lower right corner and lightly thread 2 M5 8mm screws. I'll gently slide the bracket until the middle mounting hole aligns with the hole in the dust cover and fan, and then insert another 1 1/2 inch 832 screw. Repeat these steps to position the last triangle bracket in the upper right corner, and insert another 1 1/2 inch 832 screw. Finally, slide the separator bar toward the fans, stopping briefly to pre-position the T-nuts with the holes they need to mate up with, and then push the bar fully into position against the fan, and add the last 2 M5 8mm screws into each triangle bracket respectively. I'll apply some pressure on the edge of the separator bar and fans to make sure things are lined up tight, and then crank down the set screws on the interior corner joints that secure the separator bar to the door metal. Once those 2 set screws are cranked down, I'll turn my attention to the set screws that bore directly into the separator bar, tightening them down and locking the fans into position. With both fans in place and all the screws lightly threaded, I'll close the door, reinsert the clevis pin, and tighten down all of the socket cap screws on the front of the door with the hex wrench. If you didn't notice, the black screws, which are the socket cap screws, all attach to the frame metal. The screws that actually secure the fans to the assembly are the 832 1 1/2 inch silver panhead screws. This is the right time to ensure the edges of the brackets are in beautiful alignment, so I'll continuously check throughout this step that everything looks great. To permanently secure the fans to the brackets, I'll once again open the door and add an 832 nylon lock nut to the exposed threads of each 832 screw, of which there are 8 in total. Now I'll use a mini ratchet and screwdriver to tighten each lock nut down completely. It's at this step on other frame builds that I've found the torque applied to the lock nuts can sometimes cause the door to warp just slightly enough that the closing motion is no longer smooth. I'm thrilled to report that this time around, everything opens, closes, and latches wonderfully even after locking the fans into position. That finishes adding the 2 front fans to the door, and now it's time to do a little cable management on the inside top of the door. I've designed these simple cable clasps that will keep the 2 fan cables tucked away nicely. They are 20mm tall by 20mm wide and have a 6mm boot on the bottom. A 5.5mm by 16mm pill-shaped hole allows me to position and slide the clasps up or down as needed. The height of the fan cables is roughly 1mm, and with the design of the frame door, there is roughly a 2mm gap here, and this is where I can stuff the fan cables into and have them run flat to the point where they turn vertical to run up the frame. I'll roll in a couple of T-nuts into the top bar, and then unfurl the fan cables so they are devoid of kinks or folds. Once flat, I'll gently slide them back into the small cavity under the top bar, position the clasp so the flat boot is pressed firmly against the top of the fan plastic, and tighten the screw down to trap the fan power cables out of the way from the rest of the frame. The second clasp I will position about 3/16 of an inch back from the edge of the fan. This should give me plenty of room to zip tie and route the fan cables from this point, while staying clear of the metal when the door is opened or closed. This portion wraps up the door and fan install. One quick thing worth mentioning is that with the fans in this orientation, air will be pulled in from the area surrounding the frame, and that air will be pushed over the SSDs, which will be resting directly behind these fans. Time to switch gears and work on some electrical tasks. I'll start with the cabling on the front left side of the frame, since this area's wiring will be more complicated than on the right side. There are 4 items I'll focus on here: the front panel connections, the 5V RGB signal for the distro plate, the water pump's Tach cable, and the PWM power source for the left side radiator fans. Typically, I construct specialized pass-through and pin header containers to centralize as many connection points as possible, and this build will be no different. I should mention that I don't particularly like the small 3 and 4 pin RGB header pins, and in the following steps, we'll be converting a 3-pin 5V RGB header to a Molex 2510 4-pin connector, mostly out of principle and a steadfast commitment to eliminate connectors that irritate me. Here's what I've put together in regards to the pass-through for the various wires. The main panel on the left serves as the attachment point for the other pieces. It's 4mm thick, has been printed with 100% infill, Elegoo gray filament, and also has 23 pinholes in a vertical column at the top oriented to support 2.54mm pin pitch. This pass-through box is where I'll bridge the pins from the front of the frame to the back of the frame, and the cover will simply conceal the wires inside. It has 1mm by 1.25mm pass-through holes on the front and the back, and inside there are two spines that help to guide the pins into alignment with each other once they've been inserted. To power the radiator fans on the left side of the frame, I'll be using the Singularity Computer's 2x4 PWM fan hub for a total of 8 4-pin PWM fan connections. The two smaller black pieces are surface-mounted wedges that will be used to secure the fan hub to the main panel. The fan hub has one 4-pin PWM input and 8 4-pin PWM output ports. These typically come with a strip of Velcro on the back for mounting, but I don't do Velcro, and I've already removed that from the unit. Anytime I split lots of fans from a single power source, I'll double check the amp and wattage output of the fan headers in the motherboard manual. This Oros Master supplies 2 amps and 24 watts to 4 groups of pin headers on the motherboard, and with the P12 fans each utilizing 0.1 amps and about a watt of power, along with the fact that there will only be 6 of them on this hub, I've still got plenty of unused headroom in the power delivery department. On the main body, the fan hub will sit perfectly in this rectangular area, which is flanked by 4 M2.5 threaded holes. The rectangle's interior has 3 small platforms, which the flat areas of the fan hub's PCB make contact with, ensuring that the bumps from the solder pads float inside the area around the platforms. I'll drop the fan hub into the rectangle, and as you can see, the top edge of the PCB is in perfect alignment with the surrounding rectangle. Now I'll slide on the bottom wedge, push it firmly into position, and screw in an M2.5 by 8mm screw. I'll add another screw of the same variety on the other side of the wedge. The top wedge is installed in the same manner. Slide it into position, add an M2.5 by 8mm screw on one side, and add another screw on the other side. The fan hub is now completely secured and isn't going anywhere. Now it's time to prepare the pins. I'll be using 2 links of pin headers that each have 20 40mm long pins, although the header itself will have 23 positions. This will allow me to remove a few pins to create buffer space between the remaining pins. I'll count over 23 positions on a full header strip, and using a pair of flush cutters, snip at the indentation between the pins. I'll cut 2 of these links, and using needle nose pliers, remove these pins to create 3 banks of 4 pins, and a single bank of 8 pins. I'll insert the finished section into the front of the main panel. Now I'll slide the pass-through box onto the back side of the pins, and attach the box using M3 10mm screws. Once together, you can now see how the pins rest in the spine, which helps to keep them straight and organized in the box. The mating length of the pins needs to match the kind of connectors that will be plugged into them. The bank of 8 pins will be used for front panel connections, and the mating length of these pins needs to be 7mm. The 3 banks of 4 pins are for a custom RGB header, pump tachometer, and PWM fans, so the mating length of these needs to be 8mm. Using a millimeter ruler to measure and a small scrap of 3D printing material to push, I'll massage each pin until the protruded mating lengths of each pin are correct. For reference, the mating length refers to the length of the pin that comes in contact with the connector housing to bridge the electrical connection to whatever component it is attached to. Now I'll take the second header and make sure the mating length is consistent for these pins as well. With the lengths correct, I'll push it into the other side of the pass-through box. In terms of alignment, the pins are looking great, but I need to trim off a couple millimeters from each pin. I'll take a Sharpie and put a mark on the very back of the front-facing pins where they touch the furthest guide spine, and then using the flush cutters, I'll clip the pin off at each mark. I'll reinsert the header into the front of the box, and now I'm ready to solder the pins together. In general, the more overlap there is between the pins to be soldered, the stronger and more stable the connection will be. Most of my electronic soldering tasks are undertaken with the following tools: SRA number 135 No Clean Flux Paste, a spool of 6337 rosin core 0.8mm solder, and an 80-watt digital soldering iron. Despite the solder having a rosin core, in most circumstances I will still apply a bit of flux paste to ensure optimal flow and bonding once the solder turns molten. The melting point of this particular solder is 361 degrees Fahrenheit. Before jumping into the soldering process, let me talk briefly about the pass-through box's design. The holes on the front of the box are vertically oriented 0.75mm higher than the holes on the back. This allows me to wedge the front pins below the back pins. The slight mismatch in alignment will cause just enough pressure between each pin pair that they won't need any extra clamping force during soldering. The area to be soldered is small and the solder itself has a flux core, so I'll be conservative with additional flux paste. I'll swirl a toothpick in the container and very gently apply it to the surface of the pins where they overlap. As far as soldering technique goes, I'll apply the flux paste, ensure that a small bit of solder has been pre-melted on the tip of the iron to support optimal heat transfer, contact the iron's tip with the bottom of the area to be soldered, gently run the tip of the solder coil along the surface. In short order, all 20 pins are soldered. Once the pins have cooled down, I'll gently press on each one and make sure they remain bonded and do not crack, so as to have confidence that the solder connections are fit for purpose. Outside of me getting a little pokey with my poker here, TOASTY! Everything went well. I also want to validate that each pin pair will conduct electrically from end to end. To do that, I'll take out my Klein multimeter and put it into audible continuity mode. This mode simply tests if a circuit is closed, and if so, will emit an audible beep to indicate the path is good. All 20 pins look good electrically as well. With the soldering complete, I want to create a layer of insulation on the pins. The space between the guide spines forms a trough into which I'll squirt the colloquially and literally named product, liquid electrical tape. This stuff usually comes in a dip bottle with a small brush to apply it, but I find it's easier to suck up a few ounces into a plastic syringe and then inject it between the pins. The viscosity is such that it will tack up fairly quickly, but it will also slowly seek its own level and flatten out to a degree. During application, I'm primarily concerned with getting enough material below the pins, and then as needed, I can add a little more on top as it starts to flatten out. Additionally, a flat edge tool can be used to very gently compact the material into place, but I'd encourage to do this sparingly as things can get messy very quickly with this stuff. Here's how it looks once the material has been dispersed across the pins. Like me after a proper taco meal, this is going to be runny for the next 3 to 4 hours. So like me after a proper taco meal, the assembly will set in a cool dark room waiting for things to harden up. After 12 hours, the surface has mostly solidified and remains only slightly pliable. You can see how the pins are completely coated, with the ridges showing through where the material settled. Now I'm sure these pins aren't going anywhere, are well insulated, and will perform their duty admirably. The final step is to place the cover onto the pass-through box and secure it with an M3 6mm screw in each corner. This panel is going to be placed on the back of the frame, just to the right of the reservoir. I'll roll in 5 T-nuts, 2 on the horizontal support bar, and 3 on the vertical section of the reservoir mounting frame. Initially, I'll push the top 2 T-nuts for the vertical section above the edge of the panel to make them easier to position. Readjusting the T-nuts as necessary, I'll place the panel and lightly thread a couple of M5 6mm screws. I'll leave them loose enough to easily reposition the panel as needed. With the bottom screws started, I'll use a hex wrench to push the other 2 vertical T-nuts into position one at a time and thread those screws as well. Once all the screws have been started, I'll make any final adjustments and then tighten the screws down completely. For the 2 remaining screw positions on the right side of the panel, I've printed these simple buffer cubes that measure 20mm by 20mm by 20mm. I'll roll in a T-nut, push it into position with the hex wrench, slide the first buffer cube into position, insert an M5 30mm screw, and tighten it down completely. Finally, I'll add the last buffer cube and screw to the top right of the panel. Here we are with the panel fully attached and ready to connect some wires. Looking at the pass-through box from the front of the frame, this is where the connections will all be joined and has the benefit of being in close proximity to the source header pins. Before getting to the wiring, I need to tidy up the left side radiator fans. The first task is pretty straightforward. I'm going to make sure that all of the mounting screws are the same. I think zinc-coated steel screws fit the build look most appropriately, so I'll replace any screws that aren't that type. The second task is to make sure the fan cables converge in the right direction. These 3 locations are unique since the screws will be used to trap the fan wires behind them. The top fan's cable will go behind the middle fan's top left screw, the bottom fan's cable will be trapped behind the bottom fan's upper left screw and the lower left screw of the middle fan, and the middle fan's cable will be singularly trapped behind its own lower left screw. This arrangement will see all three of these fans' cables converge together here. To bundle the cables together, I'll be using these simple clasps. They are 25mm by 20mm and have a 2.4mm wide slot on the front. The conductor cables for these fans measure 4mm tall by 0.8mm wide, so when three of those cables are turned on their side, it will fit perfectly into the opening on the front of the clasp. I'll roll in a T-nut and loosely thread an M5 6mm screw. After bunching the three fan cables together, I'll slide them into the slot, reposition the clasp as desired, and tighten the screw down completely. Turning my attention to the fans on the front left side of the frame, I'll replace any screws that don't match, and also add the Silverstone dust filters to these three fans. I'll follow the same strategy for trapping the fan cables as I did on the back. Here's how everything looks with the filters installed, the screws made to match, and the cables oriented how I want. On the back of the frame once more, I'll roll in a T-nut and secure another fan cable clasp by lightly threading an M5 6mm screw. I'll do this on the bottom of the bar, and then push it up into position since space is limited where the clasp is going to be placed. This clasp will face 90 degrees away from the other clasp and is positioned at the same height on the bar. Next is to massage and flatten the three remaining fan cables and slide them into the slot. With all 6 fan cables converging nicely, I'll work out any kinks and make sure they are sitting flush in one bundle, add a 4-inch zip tie to hold them together, and clip the end with flush cutters. I'll add 2 more zip ties here, with about ½ an inch of space between each one. With all of the fan cables bunched together, I'll plug all 6 connectors into the fan hub on the panel. There isn't any specific arrangement that the cables need to follow, but it is important to plug one of the fans into the connector labeled Fan1-RPM on the fan hub. All that's left to do for these cables is to tuck them away. For that, I'll be using these simple supports to bend and attach the fan cable loop to the vertical support. These supports are 25mm by 20mm, have 2 small holes that can be used to thread zip ties, and there is also an M3 threaded hole on the front that can optionally be used to attach a number of different styles of covers. I'll roll in a T-nut and lightly thread an M5 6mm screw. Bunching up the cables, I'll slide the support up, insert the cables, and then gently move the support back down until the cable loop reaches the desired tension. Once in place, I'll tighten the screw on the support down completely. Lastly, I'll add 3 more zip ties and snip the excess with flush cutters. The small lengths of cable that lead to the daisy chain connectors need to be managed as well. I'll position all 6 connectors behind the cable loop that was just secured, stacking them in a 2-deep, 3-tall arrangement, and add a zip tie in the middle of all the cables. Typically, I would take the time to cut off and re-add all of these connectors with exactly the length of cable needed. However, since I can't see the future and may someday want to use the daisy chaining feature of these fans, I'll be content tucking them away versus cutting them off. Finally, I'll put 2 more zip ties on the last remaining arc of cables. Now that the fan cables are all attached to the hub, I can connect the hub to the panel's bottom 4 pass-through pins. But to do that, it's time to break out the crimpers. The usual crimping suspects are as follows: a pair of flush cutters for cutting wire, a Knipex automatic wire stripper, needle nose pliers, and the items I specifically use for creating 3 or 4-pin fan cables are 24-gauge stranded wire, shielded Molex 2510 female fan pins, and a pair of PIBA 2030M micro connection crimpers. This is a single-action ratcheting crimper that crimps the conductor and insulation wings simultaneously. Between the different crimpers I have on hand, from the iWis 1442Ls, SN28Bs, SN58Bs, the Engineer Pad series, and Hosen P707, this PIBA model performs the best out of all of them for smaller connector types. To comfortably go from here to here, I'll whip up a 3-inch, 4-pin PWM cable using the materials and tools specified. I'll unspool some wire and cut 4 3-inch lengths. The female contact pins have 3mm of distance between the front of the insulation crimp wings to the front of the conductor crimp wings. So 3mm will be how much insulation is stripped from both ends of each wire. The connectors I'll use are the 4-pin, but with 3-pin locking tab style. Starting from the top wire and working down, there is ground, 12-volt, tachometer, and PWM wires. I'll position the first wire in the Knipex auto strippers and remove the insulation on both ends, and then using a millimeter ruler, validate that I have indeed removed 3mm of insulation. For the actual crimping, there are a few different strategies I employ for these specific pins. I will leave the cut tape fragment on the back of the connector pins throughout crimping, as they provide an excellent backstop which helps to align the connector in the crimper jaws. I'll insert the pin and squeeze the crimper handle until the ratcheting mechanism grips the metal. Then I'll take the wire, push it through the insulation crimp wings until it stops, and then squeeze the crimper handles the rest of the way down. Here's a close-up of how the crimp turned out. As you can see here, the insulation is compressed without excessive splitting. There is no insulation compressed by the conductor wings. The conductor strands are all straight and adequately compressed, and the conductor brush is slightly flared up from the compression of the strands. All in all, not a bad crimp. To remove the tape reel fragment, I'll pinch the tab with a pair of needle nose pliers and gently rock the connector until it breaks free. Another technique I will rarely employ is to very slightly pinch the conductor wings, so that when the wire is inserted into the connector when crimping, that insulation doesn't shift too far forward in the connector. I'd like to reiterate that I only use this in very specific circumstances, and it takes some practice to use effectively. It's very easy to mess up crimps using this approach, so take caution. The last technique I use, and this one I use almost all the time, is to pre-position the wire in the connector and then use needle nose pliers to slightly bend the insulation wings to temporarily hold everything in place. Once I've applied the slight pinch, the connector is inserted into the crimpers as normal, and the connector is crimped the rest of the way on. Crimping is an art, and part of that art comes from feeling clues through your fingers, clues from sliding the wire in, and clues from how the crimper jaw pressure feels. Now that I'm old, and post hand surgeries, accidents, etc., some of the sensation that made free crimping easier have been lost to me. This technique is a good way to get great crimps with a little bit of practice. Fan wires are notoriously easy to insert properly as long as you have fingers, eyeballs, and a real passion to succeed. Oh my gosh, this connector housing even has a watermark. This cacography on the top is a reminder of which pin is number 1, and from that the rest of the pin order can be ascertained, assuming the task of counting from 1 to 4 in order isn't a particularly challenging proposition. On each pin there is an angled ant head on one side and a small metal tab on the other. This metal tab is inserted into the housing oriented such that it will snap into one of the windowed slots. Additionally, if you need to remove one of the wires from this style of housing, insert a small object into the windowed slot, physically depress the metal tab, and then pull the wire from the back of the housing. With all 4 wires made up, it's time to insert them into the connector housing. I prefer to hold the connectors like so, and then insert each wire into the same position on each connector, top to top, second to second, etc. And here's the finished cable. Now I'll plug one end of the cable on the in port of the fan hub, and the other end on the bottom 4 pins of the custom pin header. I'll be sure to orient the alignment tabs on the connector itself to point toward the right side of the frame. Now I'll make another short cable in exactly the same fashion, but rather than being 3 inches long, this one will be 2 inches long. Once this smaller cable is made, on the front of the frame, I'll insert one end of the cable on the sys_fan4 motherboard header, and sit the other end on the bottom 4 pins of the pass-through box header, with the alignment tabs on the connector pointing toward the frame's right side. This completes the steps necessary to deliver power from the motherboard header, through the pass-through box, to the fan hub, and finally to the fans. Next up is connecting the pump tachometer cable. One thing to note here is that I'm not going to be using this pump's tach feature, as I like to run it wide open all the time. I'm simply building in the linkage now, so that if I want to use that feature in the future, it's already built and waiting. Since I only need 2 wires for a tach bridge, I'll make another cable using the 4-pin connector housing that is 3 inches in length, but only attach pins 3 and 4, which are the tach and PWM pins respectively. I'll plug one end of the newly made cable into the sys_fan5_pump header on the motherboard, and the other end onto the next group of 4 pins on the pass-through box, with the alignment tabs facing the right. Later, I'll tidy up and store the pump's tach cable on the back of the frame, but since I'm not going to be using it, that can wait till later. Now I'm going to go ahead and convert the 5V RGB cable to a 4-pin connector. I'll be using the 5V 3-pin addressable RGB header labeled D_LED1, which is found near the upper left corner of the motherboard. The only problem is, I do not like RGB headers. There's one more issue to solve. The SAS HBA has to go in the bottommost PCIe slot, and with the traditional RGB plugs being about 10 times taller than they need to be, the card won't fit into place once the cable has been plugged in. I'll fix both of these issues, but let me make the cable first. This is the RGB cable I'll be using as a base. When holding the connector ends up to each other, it's easy to assume that the pins in one connector correspond to the same pins in the other connector. It's a good idea to validate this hypothesis through test and observation. Once again, I'll grab the multimeter, put it into audible continuity mode, press the probes on what should be corresponding pins, and sure enough, the beep tells us that they do correspond in this case. I'll lay the base cable out and using a ruler, put a mark 7 1/2 inches back from the black RGB connector. Then I'll snip the cable in two using the flush cutters. Again using the flush cutters, I'll very carefully snip between the wires on the end so that I can separate each wire about 1.5 inches down. Now I'll simply strip the insulation 3mm as I did with previous cables, and crimp a Molex 2510 female pin onto the end of each of the 3 wires. Finally, I'll insert the pins into a 4-pin PWM connector, keeping the 2-pin, 1 blank, 1 pin order intact. And then using the multimeter in audible continuity mode, I'll verify that my crimp job is adequate on all 3 pins. Next, I'll address the height of the connector that attaches to the motherboard. To do that, I'm going to slightly modify a typical 5V RGB right angle pin header. Some 90-degree angle headers have designs that allow you to twist the base of the pin posts to point in a different direction. I'll twist all 3 pins 180 degrees from their starting point. Now, I'll plug the angled pins into the RGB connector. It is possible to solder the pads where the RGB angle enters the connector, but it isn't designed for that activity. It doesn't take a lot of heat to melt the surrounding plastic, but it is possible to solder these pieces together as long as you don't linger with the heat transfer process. With RGB pins being naturally brittle and very easy to break, I definitely want to create additional strain support for this cable. To do that, I'll roll in a T-nut and lightly thread an M5 6mm screw and add another cable clasp. Except this time, I'm going to turn the clasp to point down instead of up. Once the clasp is loosely positioned, I'll plug the newly minted right angle RGB connector onto the D_LED1 header, hook the cable around the arm of the cable clasp, slide it into position, and then tighten the screw down completely. Now I'll gently press a clasp cover with an 11mm buffer post into the clasp and secure the cover using an M3 6mm screw. Lastly, I'll plug the other end of the cable into the next group of pins on the pass-through box, with the alignment tabs on the connector pointing toward the left of the frame. And that wraps up the RGB, tachometer, and fan hub connections on the front of the frame. As a special bonus, the HBA has now developed the common courtesy required to fit beautifully over the top edge of the motherboard side RGB cable. There's one more short cable I need to make before I shift to the back of the frame to finish up the connectors for the pin header. The reservoir unit comes with this 3-pin RGB to 3-pin JST cable to connect the strip to an RGB header. I'll use my multimeter to test the pin grouping and then cut the 3-pin RGB connector off with the flush cutters. Then I'll strip the insulation back 3mm, crimp the pins, and slide them into a 4-pin PWM connector. With that simple task out of the way, we can finish up the connectors and cable routing on the pass-through panel. Another beautiful example of undoative work. I'll remove the second screw down from the top of the panel and add another cable clasp back in its place, along with a slightly longer M5 10mm screw. Since the power cable and the Tach cable for the pump are going to go in opposite directions, I need to separate the 2 cables from the sleeving. To do that, I'll very carefully insert the tip of the flush cutters under the heat shrink and snip upward until a full-length cut has been made. Next, I'll pry the heat shrink from the cables and sleeving, and then use scissors to cut the sleeving all the way back to where the cables meet the pump. I'll go ahead and plug in the distro plate's RGB connector that was just made, and then below the pump, I'll roll in another T-nut and add one more cable clasp with an M5 6mm screw. With the clasp in place, I'll drape the distro plate's RGB and Tach cables over the support arm, slide the clasp so the left edge is directly under the right side pump cover line, and tighten the screw down completely. These wires are now ready to be routed to the panel. The path these 2 cables will take is along the bottom of the distro plate, up the right edge, over the cable clasp, and into the pin header. Now that the cables have been situated, I've also taken the liberty to add a few 4-inch zip ties here, and on the front of each cable clasp, I've used covers with an 11mm buffer, and have attached those using M3 6mm screws. As I mentioned earlier, I'm not going to be using the pump's Tach cable, so I'll unplug it and tuck it out of the way. I think at this stage it's time to test if everything is working as expected. I've already attached the computer power cables needed to execute such a test. When I press the power button, we should see the distro plate RGB come on, all 6 fans on the left side radiator come on, and the pass-through box not explode.
Oh boy! Yay!
What a beautiful day in the neighborhood. The front panel connections for the switches and LEDs are going to have a special harness made a little later, but I can go ahead and connect those wires from the motherboard to the pass-through box on the front of the frame. A quick way to save some time if colored wire is acceptable is to purchase some multicolored breadboard jumper wire ribbon cables and separate out a few pairs. For this build, I prefer to keep the darker, more monotone color palette going, so I'm going to make my own cables using black wire. I'll use the same 24 gauge stranded wire for these cables as I did for the fan cables. I'll be using the labeled front panel housings for these connectors, and the pins are commonly referred to as 2.54mm female DuPont pins. The insulation wings on these pins have an offset, with one sitting a little farther forward on the pin body. Depending on the crimper and the technique used, this can cause some alignment issues. This is another circumstance that I found can be alleviated by leaving the cut tape fragment on the back of the pin during crimping. The distance between the front of the insulation wings and the front of the conductor wings is 2.5mm, so that should be how much insulation is stripped from each end of the wire. To complete these cables, I'll measure and cut 4 lengths of wire that are 5 1/2 inches long for the hard drive and power LED cables, and 4 lengths of wire that are 6 inches long for the power and reset buttons. The crimping procedure for these cables is nearly identical to the crimping for the fan cables. Strip 2.5mm of insulation from the ends of each wire, pre-align the wire in the female DuPont pin, gently compress the insulation wings on the pin to temporarily hold the pin in position, insert the pin into the crimper, and compress. And like Tony, it's dungy. Now, just insert the finished crimp into the connector housing and rinse and repeat until all the cables have been made. These cables can be added directly onto the front panel, or FP pins, here. In my case, I'm going to be using these cables to bridge the front panel pins on the motherboard to the remaining 8 pins on the pass-through box. Gigabyte includes something called a G connector with some of their motherboard models. So when I was reading the What's in a Box section of the manual and saw G connector, I was just like you and thought this was a reference to a free trial voucher for a Metropolitan Friend Finder service. But no, it's just this little piece of plastic. However, I personally find this little piece of plastic quite handy in securing the front panel cables in a tidy way. The connector has label and wire orientation markings for common front panel connection types: power button, reset button, hard drive LED, power LED, chassis or case intrusion, and speaker. I'll take each of the cables that were just made and slide them into the housing, making sure to keep the positive and negative indicators matching those coming from the motherboard. You simply press the connectors in one at a time until the small latches on the G connector snap into place on the back of each housing, and once all the cables are inserted, push the G connector into the front panel pin header area on the motherboard. Since the connector is polarized, it can only be inserted one way. Once the G connector is in place, I'll insert and arrange the connectors onto the pass-through box. From the top down, it will be power button connector, reset button connector, power LED, and then the hard drive LED. While it doesn't matter a whole lot, I like to position the connectors with the labels all facing the same direction. In this case, that means facing the left. Now that all the front panel cables are in place, I'll add a few zip ties for organization, and this task will be complete. As I mentioned earlier, I'm going to be creating a special harness and splitter for these connections so that I can control the machine from multiple locations. But for this video, this is as far as I'm going to go with the front panel cables. Next up is to build the 3-pin cable that will power the Barrow digital Flowmeter. This is essentially another fan cable, so the same Molex 2510 female pins will be used again, along with the same tools and crimping techniques. However, the connectors on each end are the 3-pin fan connector variant. The length of the cable to be made is 16 inches long. I'll plug the connector into the bottom of the Flowmeter and then push the cable up and behind the GPU tubing. I'll lightly attach a 4-inch zip tie to provide some support for the cable as it travels along the pipe. Now I'll undo the cover from the cable clasp holding the RGB cable, insert the 3-pin cable into the support arm, put the cover back on, and rethread the screw. All that's left is to put a small bend right in front of the connector and then plug it into the sys_fan3 header on the motherboard. To me, it feels good to wrap up a lot of these smaller power delivery build tasks, but I think that's going to do it for this video. After consulting with my legal and marketing departments, they are insinuating that I need to retire. Something about me being an old man trying to play a young man's game. The 12th track's title from Daft Punk's Tron Legacy soundtrack may speak to the situation. But I keep having these peculiar dreams about crimping 16-pin power cables for the RTX 4000 series, building a delivery grid for motherboard and GPU connections, eating more pineapple, and finishing this build. I'm not sure how these elements coalesce into one stable reality, but for now, I hope you've enjoyed this demonstration. Thanks for watching, and out.